So the Stirling numbers of first kind are defined as follows. The absolute value of the Stirling number of first kind with parameters n and k is a number of permutation in Sn that are product of exactly k disjoint cycles. And the Stirling number itself, Snk, is a signed version of this of its absolute value. So Snk will be -1 to the power n minus k time its absolute value Snk. And last time we computed some of these Stirling numbers for some values of n and k, and we also proved this formula that the following factorial Tn, which I recall here is defined as Tn is the product of n factors starting with t minus 1, t minus n plus 1. When you expand this in powers of t, the coefficients from k equals 1 to n are going to be the Stirling number of first kind. So this is the result here that we proved last time. We then define Stirling numbers of second kind, and these Stirling numbers also have two parameters, n and k, and Snk, capital Snk is defined as the number of partitions of a set with n elements into k parts, and here we assume that the parts are always non-empty. And we also proved using induction on n that when we expand t to the n in terms of these following factorials from k equals 1 to n, the coefficients are going to be the Stirling numbers of the second kind. And one more thing we proved last time, we actually showed that k factorial times Snk equals the number of surjective functions from a set with n elements to a set with k elements. And from one of our previous lectures, we know that that number can be calculated using the inclusion and exclusion, and we get this formula that the Stirling number of second kind can be written as this alternating sum. Okay. So today we'll do a bit more about this number. So one thing that one can prove with the Stirling number is determining their exponential generating functions, and I'll just do it for one of them. So I'll write so for the Stirling number of second kind, we have this formula given before. And one can, if we define its exponential generating function, let's call it f of t, which is the summation over all n0 to infinity of s and k times n factorial t to the n. We then can obtain the following result. F of t, sum from, I just copy now the definition, n factorial times t to the n. And now this expression from the top in red comes into play here, and we get, you can take the k factorial. So here n is it's the parameter that's changing, k is fixed. So you can take 1 over k factorial as a common factor, and it's a summation from n equals 0 to infinity, and then it's a sum from j equals 0 to k of k choose j minus 1 to the j, k minus j to the n, t to the n here, and everything divided by n factorial. And this can be written as summation. So 1 over k factorial summation from n equals 0 to, well, no, we change summation here. Here we are going to change the order of summation. So it's summation from j equals 0 to k of k choose j minus 1 to the power j. And here we have summation from n equals 0 to infinity of k minus j to the n, t to the n divided by n factorial. The first part stays the same. And we but we can evaluate this inner sum here. And this inner sum gets replaced by e to the k minus j to the power t. And applying the binomial formula here, we will get the following result: 1 over k factorial e to the power t minus 1 to the power k. So essentially what we proved is this expression, summation for n equals 0 to infinity of s and k over n factorial t to the n equals 1 over k factorial e to the t minus 1 over k. So one can determine the exponential generation function of the Stirling numbers of second kind. And I won't prove it here, but from this result, using the previous results on the previous page about the relation between the coefficients of these expansions and the fact that a matrix containing the Stirling numbers of first kind is the inverse of the matrix containing the Stirling numbers of the second kind, one can get the exponential generating function for the Stirling numbers of the first kind. So you have a result of the following: summation from n equals 0 to infinity of s and k n factorial t to the n equals log of 1 plus t to the power k, so outside log, divided by k factorial. Okay, so this result is done in the book. Okay. Now another sequence that is studied in combinatorics is the sequence of Bell numbers, and that is defined as follows. So Bn, this is usually called the nth Bell number, is the number of partitions of a set with n elements. Okay. Now remember that S and K was the number of partitions of the set n into k parts. So one can get immediately the result that Bn is the sum from k equals 1 to n of S and k. So that's a immediate consequence of the definition. Now let's calculate the parameter Bn for some small values of n. So n here and Bn here. When n is 0, it's just the empty set, so it's just, that's it equals 1, B0. Now, if you have a set with one element, there's only one partition of it, so 1. If you have a set with two elements, there are two partitions, one in the singletons and one the set itself. That's 2. Now, if you have three elements in your set, there are various partitions, and I'll leave you to count that there are 5 of them, 5 partitions. And 4, 5. We'll see in a second how one can calculate these numbers. Now, there's no nice formula for the number for these Bell numbers, but there is a recurrence relation for the Bell numbers, which I'll prove right now. So proposition. For n, let's say greater or equal to 2, Bn is a summation from k equals 1 to n minus 1, choose k minus 1, Bn minus k. Okay. And that can be written as a summation, if we change the sum, as a summation from L equals 0 to n minus 1 of n minus 1, choose L, BL. So you can express Bn in terms of all the other B's. So I'll just prove the first part, and the second one can be done similarly. So when we calculate Bn, we look at the partition. We have our set n, and let's write it as a bunch of a partition into some kind of sets. Let's say A1, AR, A1, A2, AJ, AR. And now one of these sets contains the element n. Let's say the element n is there. So this AJ, the part that contains n, is n union something else. Let's say AJ prime. Okay, and let's just say that the cardinality of AJ equals k. Okay, so now when we count, so this is the same as cardinality of A prime J is k minus 1. So now when we count Bn, when we do the calculation for Bn, we look, okay, let's choose the k minus 1 elements here that we will add to the element n. So that can be done in n minus 1 choose k minus 1 ways. And what do we have? If we look at the part here with if you have a partition A1, A2, AR of the set n, and you remove n from it, we remove the whole set actually containing the part that contains n, then we are going to have a partition of the remaining n minus k set. Now, how big can k be? K could be as small as 1 in the case that the element n is by itself. So it can be a small sum from k equals 1. And k can be as large as n in the case that the partition consists of only one block. So that's essentially the proof. And the second one, it changed the summation from here to here. I think you denote L equals n minus k. And that gives the second result. Now, here's a procedure to calculate this number quicker than using that recurrence formula. And this is called the Aitken array or the Pierce triangle. And so the procedure is the following. You start with 1, which is B0. And then B1 is what? B1 is 1. And from these two numbers, as we go in this direction, we add them up, we get a 2. And now, when we start the next row, we move this, we move these 2 here at the beginning. So that's a 2. So that will be B2. And we construct the numbers on this row the same as before. So in this position, we look to the left. So if we are in position here, we look to the left, we see a 2, and we look to northwest, and we see a 1. So we put a 3 here. Similarly, from these 2 and from these 3, we get a 5. And now with this 5, we bring it back here, and it turns out we put the 5 here, which turns out to actually equal B3. So, so if we repeat this procedure, this is 5. On the first position, we'll always get the Bell numbers. So let's try it one more time. So we have a 2 and a 5. So that gives us a 7. 3 and a 7. That gives us a 10. And 10 and a 5 gives us 15. And it turns out that this 15 is actually B4. And I'll leave it to you to calculate other numbers in the sequence, B5, B6, and so on by the same procedure. It's pretty neat. Now, in terms of asymptotics, so like I said before, the Bell number doesn't have a closed formula. It has actually, to determine the asymptotics is actually a pretty complicated matter, but that has been done, and I think Bn, so is asymptotically, if I copy this formula right, n to Wn to the power n plus 1/2 divided by square root of n times e to the n over Wn minus n minus 1, where this Wn is satisfy the property that Wn times e to the power Wn is n. So from here, Wn, you can think of it as being something like log, natural logarithm of n. So if you unpack this complicated formula, the Bell number has an exponential growth. It grows very fast. Okay. Now, let's look at some other combinatorial quantities that look similar. So one of them, so let's look at partitions. And let's define the following. Pkn is the number of solutions x1, xk. So we have k parts. N equals x1 plus xk, and x1 is greater or equal to xk greater or equal to 1. So it's number of these order k tuples that are greater or equal to 1 that add up, sum up to n. So we can do some small examples. You can see what is P3 of 7. Well, how can you write 7 as a sum of 3 numbers? So the largest we can put is 5. 5 plus 1 plus 1, that's 1. You can do 4 plus 2 plus 1. 3 plus 3 plus 1. And there's one more, 3 plus 3 plus 2. So there are 4 solutions, so you get this. Okay. What values can we find for pkn? What about p1n? Well, that one is not too difficult. It's just one solution, x1 equals n. And I'll leave it as an exercise for you to figure out that p2n is the number of solutions where k equals 2, and claim that that is going to be something like floor of n over 2. Okay. Now, in general, for pkn, for fixed k and n going to infinity, one can actually figure out the asymptotics of these values. So if k is fixed, pkn behaves something like n to the power k minus 1 divided by k factorial times k minus 1 factorial. So this is an exercise of one of the previous homeworks, and you can find its solutions in the notes. So I won't prove it here. You can, this solution of this exercise can be found using the number of compositions and recompositions of n into k parts. Now, let's look at a different parameter. It's denoted Pn. This is the number of ways we can write n as the sum of some natural numbers with order not important. So it's the number of partitions of the number n into smaller, as a sum of smaller numbers. So let's see some examples. So n, Pn. When n is 1, 1 is 1, so that's one way. N equals 2, you can write 2 as 2, or you can write it as 1 plus 1, so there are two ways. 3, here the order is not going to, the fact that the order is not important plays a role, because 3, you can write 3 as 1 plus 1 plus 1, also as 1 plus 2, and 1 plus 2, for us, it's the same thing as 2 plus 1. And it's, we can write 3 as 3 itself, so you have three ways. And then for 4, we have as before 1 plus 1 plus 1, 2 plus 1 plus 1, 3 plus 1, 2 plus 2, and 4. So there are 5 ways. And I leave it to you to figure out that 5. You can, it's P5 is 7, and so on. Okay. Now, the study of this partition number goes back to Euler. So one way you can interpret when you look for Pn, so you're counting the number of solutions of this equation, n equals maybe 1 plus, you have 1 a bunch of times, plus 2 a bunch of times, and so on, plus maybe k plus k. K could be some number. So here we have this one is taken a1 times, 2 is let's say a2 times, k is ak times, and so on. So Pn, so any solution of this equation of any partition of n has this form. So when we count it, we get that Pn is the number of these tuples, which essentially count the multiplicities of 1, 2, 3, and so on. So a1, a2, and so on. And what property do they have? Well, from the equation above, you get that n must equal what? 1 times a1 plus 2 times a2 plus, and so on. And what properties do these numbers have? They have the property that a1, a2, a1, a2, so on, all of them are greater or equal to 0. And another property is that finitely many of them are non-zero. So as an example, in this, for this sum, 3 equals 1 plus 1 plus 1, 3 times, a1 is 3, and all the others, aj is 0 for any j greater or equal to 2. For this decomposition 1 plus 2, you have that a1 is 1, a2 is 1, and aj is 0 for any j greater or equal to 3, and so on. You get the picture. Okay, so it's just a matter of keeping track of each number, how many times it appears. But that can be quite useful because of that. So this is a result due to Euler. So let me rewrite here first that Pn is the number of solutions, a1, a2, so on. The property that n is 1 times a1 plus 2 times a2 plus so on. a1, a2 are greater or equal to 0, and finitely many of them are non-zero. And this fact has an interpretation in terms of the generating function of the partition number. So it's summation from n equals 1 to infinity, Pn t to the n will equal an infinite product. And that product will be something of the form 1 plus t to the power 1 times 1 plus t to the power 1 times 2, and so on. Then will be 1 plus 2 t to the power 2 times 1, t to the power 2 times 2, and so on. The next, let me put it here, the next factor will be 1 plus t to the power 3 times 1 plus t to the power 3 times 2, and so on. So Pn is the coefficient, so Pn is the coefficient of Tn into this infinite product, but this infinite product can be rewritten as follows. Each of these factors is a geometric form of power series. So the first one is 1 over 1 minus t, the second is 1 over 1 minus t squared, the second is 1 over 1 minus t cubed, and so on. So the formula is summation from n equals 1 to infinity Pn t to the n is the product, let's say, from m equals 1 to infinity of 1 minus t to the n. Okay. So, I mean, this is a very nice equation, and despite this nice equation, there is no nice formula, no simple closed formula for Pn. I'll give you in a second one application of this this fact about generating functions, but we say that this is a, studying Pn is a serious matter, and by the work of Hardy and Ramanujan, using complex analysis and the so-called circle method, they determined the asymptotics of Pn in 1917, and it's about something like e to the power pi square root of 2n over 3 divided by 4n square root of 3. So that's the asymptotics of this parameter Pn. Now, so the previous equation, we can, so we have this generating function, ordinary generating function of the partition number. It can be written as an infinite product. We can apply these methods, the idea of this proof for something else. And what is that something else? Here's the following problem. Let's look at un. Define this as the number of partitions of n into unequal parts. And let's look at on, which is defined as the number of partitions of n into odd parts. Okay, so let's do some example first to see how these numbers look like. So I have here n, un, on. When n equals 1, there's only one partition into 1, and that's an equal part, and it's also odd. When n equals 2, the partition into unequal part is 2 equals 2, so that's one way. And odd is 1 plus 1, so that's the same. When n equals 3, the partition into unequal parts is 1 plus 2, or 3, so there are two such partitions, and the odd ones are 1 plus 1 plus 1, or 3, so there are two parts. Okay, when n equals 4, unequal parts 1 plus 3 and 4, so there are two ways. Odd parts is 4 equals 1 plus 1 plus 1 plus 1, and also 1 plus 3, so there are two parts. One more, stop, 5. Unequal parts, that would be 2 plus 3, 1 plus 4, and 5. So there are three such partition. Odd parts would be 1 plus 1 plus 1 5 times. 5 itself, and 3 plus 1 plus 1. So there are 3 parts. Okay, so maybe we are onto something. So let's prove the following proposition, actually. That these two numbers are the same, un and on. The number of partitions of a natural number into unequal parts, it's the same as the number of partitions of that number into odd parts. So how do you prove that? Well, we'll show that their generating functions are the same. So we look at sum from n equals, we can take 0, un t to the n. And so by an argument similar to the proof of this result, so here we need to use different parts. So I claim that this un will be the coefficient of t to the n in the following infinite product, will be the product from m equals 1 to infinity of 1 plus t to the power m. Because in this product on the right side, when we calculate a term coming from this product, it means we pick a t to some power from finitely many brackets, and now all those powers are going to be distinct, and they're going to correspond to a decomposition of n into unequal parts. So that's essentially the proof that un is the coefficient of this of t to the n into this infinite product. So okay, so that's one part. What about the other generating function? So if we look at summation from n equals 0 to infinity of on t to the n. So this one is a decomposition into odd parts. So we'll do something, again, similar to what we did here. So here, when we did the generating function of Tn, we took all these geometric formal power series that had multiples of 1 in the exponents, multiples of 2, multiples of 3, which corresponding to the types of numbers that we could use in our decomposition of n. And now here, when we do odd, we cannot use 2s, we cannot use 4s. We only allowed to use odd parts. So it means that by essentially the same argument, that this formal power series will be the same as 1 plus t powers of t whose exponents are multiples of 1. And then similar formal power geometric power series in which the exponents are multiples of 3. And then you continue t5 to the 1, 5 times 2, and so on. So this is the same thing as the product. Let's use k from 1 to infinity of 1 over 1 minus t to the power 2k minus 1. When k equals 1, we get 1 over 1 minus t. When k equals 2, we get 1 over 1 minus t cubed, and so on. Okay, so we have, maybe if you want it, you can write like this: 1 by t minus t cubed minus t fifth. And let me write below the one that we had before, summation from n equals 0 to infinity un t to the n, which was 1 plus t, 1 plus t squared, 1 plus t cubed. And now, so to finish, what we like to do is we would like to prove that these two things here are the same. And to do that, we prove that these two infinite products on the right are the same. And how does that work? Well, we can start from the bottom one. You have 1 plus t is 1 minus t squared divided by 1 minus t. 1 plus t squared is 1 minus t to the 4, 1 minus t squared. 1 plus t cubed is 1 minus t to the 6, 1 minus t cubed. and so on. And when you multiply them together, we get that the product of all these factors, which is the same thing as this one here, will equal, things will start canceling out. So you'll have 1 minus t squared cancels 1 minus t squared, and 1 minus t4 will cancel with the next one that comes here, where we have 1 plus t4, 1 minus t to the 8th, 1 minus t to the 4th. So this one will cancel here, and so on. And we end up with exactly this product over there. So that's a proof using generating function that two combinatorial quantities are the same. Okay. Now, when we write, so let's talk a little bit about things called Ferreros Diagram, or sometimes called Yam Diagram. And this is a pictorial way of representing a partition, so of a natural number. So before, we had 7 equals 4 plus 3. Well, I guess we had a bunch of decompositions. So let me see, 4 plus 3, or I can do 5 plus 1 plus 1, or 3 plus 2 plus 1 plus 1. There are many ways to write a partition of 7 into other numbers. So when we to each of these partition, we can represent it graphically as follows. So we order the terms of the sum decreasingly, and then for you put, so we have the first one is 4, so you do 4 blocks here, and below it you put the next term, which has 3 blocks. So 4 plus 3 can be represented graphically like this. Similarly, 5 plus 1 plus 1 can be represented graphically as follows. You have the 5 there, you have the 1, you have the 1. And then 3 plus 2 plus 1, you have the 3 there, you have the 2, you have the 1, you have the 1. So this is a very simple, it's a very simple notation, and a graphical representation of this of these partitions, and but it's quite useful, and can prove things related to it. Now from these partitions, what I want to talk about, and I'll just give the definition, and we'll do the rest in the next lecture, is the notion of a Young tableau. So in a Young tableau, what we're going to do is a Ferreros diagram or Young diagram, in which we so we have a Young diagram with n squares, and we fill the squares with the numbers 1, 2, all the way up to n. So each square gets one of these numbers, and the rule is that the entries in each row and in each column are increasing. Okay, so let's do some simple examples. Let's say n equals 3. If I have this simple Yam diagram, the only way you can fill it up so that the entries are increasing is 1, 2, 3. Okay. Now, if we have a different one like this, then you can do 1 here, 2 here, 3 here. Or you can do 1, 3, 2, and so on. Okay. Let's see for the ones on the top. If we have the entry first to the right, we can do the easiest way could be you could do 1, 2, 3, 4, and then you can do a 5, a 6, and a 7. But there are other ways that you can fill it up. Okay. Here, for example, again, you can do a 1, 2, 3, 4, 5, 6, 7, and so on. So the problem that we'll study, and we'll do this next time, is to, so look at the Yam Tableau. So if we have some Yam Tableau, we have n entries, and let's say in the first row we have n1 entries. Here we have n2. Here we have n3. Dot, dot, dot. Here we have nm, and clearly we have this. So we'll have n equals n1 plus n2 plus nm, and we have that n1 is greater or equal to n2 is greater or equal to nm equal to 1. So what we'll do next time is actually we'll figure out the number of Yam tableaus of this type.